Hello everyone, my name is Ben. Today I'm going to present on supermassive black hole. So these are the contents that I will be covering today. Mm. Well, the story of supermassive black hole should really begins with quasars. The study of supermassive black holes is actually closely linked to the observation of quasars. A quasar is actually some star-like object that is observed in the skies that also emits strong radio wave. In the 1950s, the first quasar 3C273 was observed. It was identified as the bright nucleus of galaxies. When scientists at the time looked at the spectrum of 3C273, they were actually puzzled because they could not be sure what the element does the emission line correspond to. However, the scientists soon realized that the emission lines were simply that of hydrogen, but with a very high redshift of Z equals to 0.158. This value of redshift actually implies that the quasar was very far away from us at a distance of around 680 megaparsec. It was actually quite surprising that this quasar was that far away from us. Now, given the apparent brightness of the quasars, the large distance actually tells us that the quasar was in fact extremely luminous. It is radiating a power over 10 to the power of 38 watt. The high luminosity also means that the quasar has a large energy output, and scientists soon reached consensus that this larger energy output indicates that the quasars are actually powered by massive object via an accretion disk. Well, what is actually an accretion disk? When an immense amount of matter falls into a very massive object by gravitational force, it will actually spirals around the massive object before entering it, and thus forming a disk-like object. Typically, part of the great amount of gravitational potential energy is going to be converted into thermal energy and then into radiation energy, which will then be carried away by photons. Since the gravitational potential energy could be very huge because the object could be extremely massive, the disk could be very luminous. Then we wish to know how massive really is the object. The mass is typically estimated using Fourier relations. The rotating motion of the accretion disk causes the line spectrum to shift due to Doppler's effect, and that shifting corresponds to a width of the spectral lines. We can estimate the rotating velocity of the accreting disk by observing the spectrum of the disk. For example, the rotating velocity of the disk in the central region of M87 is estimated to be around 690 km per second by analyzing its spectrum. And by Fourier theorem, the mass of the object at the center of M87 is around 2 times 10 to the power of 9 solar mass. Wow, it's actually very heavy. The heavy mass reveals that there's a presence of supermassive black hole at the center of M87. Well, in fact, we can also do similar analysis to the spectra of gas and stars in the central regions of a lot of other galaxies, that actually reveals that most, if not all, bright galaxies harbor a supermassive black hole at their center. So supermassive black holes are classically defined as black holes with a mass above 10 to the power of 5 solar mass. Today, the Event Horizon Telescope even took photos of the supermassive black holes with their accretion disk. The presence of such massive objects also raises questions. Why is it there? And how does it come to existence? A famous question regarding its existence is the timescale issues. So what is the timescale issues? Well, scientists mainly believe that the supermassive black hole grow primarily by rapid gas accretions, as we have shown in the previous slides. However, scientists also typically believe that the growth rate via gas accretion is also limited by Eddington limit. That really means that the Eddington limit describes the maximum rate at which a black hole could possibly grow. So what is an Eddington limit? An Eddington limit is reached when the outward radiation pressure force on the infalling gas matches the inward gravitational force. And there exists a maximum accretion rate for the black hole, which is called the Eddington rate. And the Eddington rate is given by equation 2. Now, if the growth rate is greater than these values, it typically means that the gas will be accelerated outward as they are repelled by the outward radiation pressure force, and hence the accretion will be stopped because no gas can further goes inward. That means accretion can only happen when the rate is under this Eddington limit. Now, if the accretion is limited to this rate, then we can estimate the timescale for the growth to the black hole mass using equation 3. To get a rough idea of how large the timescale is needed for a supermassive black hole to be produced, we can substitute in some reasonable fiducial values. And by choosing these values, we can roughly estimate that the magnitude of the timescale should be around 1 gigayear. 1 gigayear is actually approximately the age of universe when the redshift is equals to 6. However, that raised some concerns because from Quasar survey, we observed that there are actually quite a handful of supermassive black holes that has redshift greater than 6. And the calculation we just did indicates that it could take roughly the age of universe at that redshift for the supermassive black hole to be formed. So how can this kind of high redshift black hole be there if it really takes more than the age of the universe at that time to form it? So this is the famous timescale problem. Now scientists have proposed many answers to the timescale issues. Here we are going to talk about two of the ways that supermassive black holes at high redshift could be formed. Firstly, it could be possible that the assembly for the supermassive black hole can be accelerated when another black hole merges into it. This is not something impossible. We have actually observed such events through detecting their gravitational waves. Mm. But, however, in these scenarios, scientists also doubt that the merger of compact objects could trigger a very strong gravitational waves, and these strong gravitational waves could kick the reservoir of dense gas away from the black hole and subsequently stop the process of accretion. This could really hinder further growth of the black hole. So could a supermassive black hole really be formed in this way? People have some doubt in it. Now, another possibility for the supermassive black hole to form is related to super Eddington accretions. In 1970s, Begelman first proposed that the effect of photon trapping could lead to super Eddington accretions. In simple words, the very reason why there's an Eddington limit is really because there's a radiation flux that will push the accretion gas outward, and this could kill the process of accretions. However, photon trapping is an effect that could reduce this kind of radiation flux. That's why a growth rate past the Eddington limit could possibly be achieved. Photon trapping comes to effect when the radial gas inflow speed is faster than the outward photon diffusion speed. This really means that this effect could happen within a certain distance to the accreting black hole, called trapping radius. And the trapping radius is demonstrated in equation 5. Further calculation shows that the growth rate of black hole is actually unlimited as long as there's correspondingly large amount of inflowing gas coming from large scales down to the vicinity of the black hole. Scientists have also done quite a lot of numerical simulations to prove that it is indeed possible to go past the Eddington limit. So here I'm showing 3 researches that scientists have done. Now this really means that as long as there is enough fuel, the black hole can grow in a rate as fast as it wants. Then, how did such growth happen? Like, how did it start, and where does the fuel supply that can maintain over several orders of magnitude growth in mass comes from? And a popular hypothesis is presented here. So based on the popular lambda CDM models, scientists suggest that in the early universe, there are actually dark matter mini halos, and those dark matter mini halos attracted gravitationally normal matter to attach to it and brought about the birth of the first stars, which is the POP3 stars. Notice that both Jeans mass and accretion rate increases with temperatures. Now, Jean mass is the total amount of mass that could collapse to form a compact structures. A high Jean mass typically means that the star result from the collapse of the gas will be very massive, and a high accretion rate guarantees that such massive star could be produced effectively. Since the gas in the halo remains relatively warm in the early universe, it has a large Jeans mass and large accretion rate. As a result, these POP3 stars produced were actually very massive. We're talking like about 100 solar mass. And these massive pop-3 stars are expected to be relatively short-lived. We estimated that they only lived for around 10 to the power of 6 years. And upon collapse, they become seed black hole of mass ranging from 10 to 100 solar mass. And if this seed black hole happens to be in special atomic cooling halos with chemically pristine gas, they could grow in a super Eddington rate. So they can eventually grow up to 10 to the power of 5 to 6 solar mass. And from that on, they can even continue to grow to become a more heavier object in a more leisurely rate. And that is really how a supermassive black hole is formed. So that is the end of my presentations. These are the references I have used. Thank you everyone. Bye bye.